Q stands for the amount of thermal energy. Let me emphasize that that is a energy, right? And now this brings us back to energy is conserved, right? And we're going to get to that a little bit later. This is just one form of energy. M, mass in kilograms, that's our base unit. Specific heat, that's going to be in terms of joules. I mean, look at right here for our units. Joules per kilogram Kelvin. Joules per kilogram Kelvin. Okay. Now, you do have an advantage here. It's delta T measured in change in Kelvin, right? But change in Kelvin is the same thing as change in degrees Celsius. Change in Kelvin is the same as change in degrees Celsius. Let me show you what I mean. I'm going to heat something up from 0 degrees Celsius to 20 degrees Celsius. That has a delta T of 20, right? Delta T. Okay, let's do that. Kelvin. This is 273 Kelvin. What's the next one? 293. Once again, that gives us a change of 20. Okay, so you could technically use Celsius in this equation, and it would work out for you because the change in is going to end up canceling it all out. Okay. All right. So a problem. Kind of a simple flow charter. A 25 gram piece of brass, C, 3.8 times 10 to the second. By the way, there's that chart in your book that I showed you where you can get these things from. Is given 730 joules of heat. If it started at room temperature, what is the final temperature of brass? So delta Q equals MC delta T. Q equals M capped. It's given 730 joules, mass 0.025. Check that out. Got to convert to kilograms. Okay. I must convert to kilograms. Specific heat is given to us. 3.8 times 10 to the second. Now, change in temperature. That is T final minus T initial. T final minus T initial. That's what change in means, final minus initial. So, room temperature is about what, somebody? Sorry? No, not 30. 18? Nope, kind of in between. 20, 22. Somewhere in there is around room temperature. We'll take 22. Okay? I'm looking for its final temperature, minus 22. And I'm going to get away with the trick that I just showed you right here. The change in Kelvin is the same thing as the change in degrees Celsius. I just plugged degrees Celsius into this equation, even though C was given to me in terms of Kelvin. I'm about to get away with it. Change in IP. Okay. And now it's just out, right? So I'm going to have 730 divided by 0.025 times 3.8 10 to the second equals TF minus 22. Need to add 22 over. So whatever 730 divided by 0.025 times 3.8 10 to the second plus 22. That'll give you TF. Final. What's it come out today? 99? 99 degrees Celsius. Got warm. Got warm. Sorry? Small. Yes. Yes, that would definitely work. Yeah. Here's the change in idea. because the change in, I put Celsius in, I'm going to get Celsius out. I'm cheating, granted. Granted, I'm cheating here. It would be better to put Kelvin and I'd get Kelvin out, but think kind of common sense here. We got a 96, right? We got a 96 out of it? 99? Is that 99?
Yeah.
Degrees Celsius out of it, or 99? What's that going to be, Celsius or Kelvin? Well, if it's turned out 22 degrees Celsius, right, that would be 295 Kelvin. It's not going to cool down to 99 Kelvin, right? 99 Kelvin is very, very cold. Very, very, very cold. Okay? So this is coming out in degrees Celsius, 99 degrees Celsius. Okay? And I'm being completely upfront with you. Plugging Celsius into this is cheating. Okay? But it's a cheat we can get away with every single time. All right, thermal equilibrium. What's that sound like? Same temperature. Things reach the same temperature. Okay? Things reach the same temperature. This happens through our three ways to transfer thermal energy: conduction, convection, and radiation. Okay? Things reach the same temperature. Now, it's all about energy, meaning that one thing loses energy, and the next thing gains the same amount. Whatever energy object A loses, that's how much energy object B gains. Conservation of energy. That's how we get to this thermal equilibrium. One thing, the hot thing, loses energy. The cold thing, by the way, I'm saying hot and cold is relative. Okay, absorbs the energy. Okay, hot thing loses energy. Cold thing absorbs energy. All right. So I'll do the first one, and I'll let you do the second. "340 grams of boiling water is added to 490 grams of room temperature water." I'm saying room temperature currently is 22 degrees Celsius. What is the final temperature of the water? Well, right now I know that whatever energy the hot water loses, that's how much energy the cold water is going to gain. That makes sense? How much the hot loses, that's how much the cold is going to gain. Now, I have an equation for delta Q. What is it? MC delta T, right? So now I can plug that. I've got negative. I'm going to use brackets just to make sure that I understand this. MC delta T of the hot equals MC delta T of the cold. All right, let's try to substitute some numbers in here. Negative mass of the boiling, 0.340. Notice it's in grams. I'm converting back over to kilograms. Times C, right?
Because it's going to be the same side.
Okay, good. We could actually cancel out these, right? It's going to be the same on both sides. They'll divide out. Now, if you need a C, right? Like C of water is always going to be 4.18 times 10 to the third joules per kilogram Kelvin. That's given to you in your book. It would be good to have that in your head. 4.18 times 10 to the third joules kilogram Kelvin. We'll divide it out, so I'm just going to leave in C right now. C times now delta T. T final, the final temperature. That's what I'm looking for, right? T final minus T initial. What's boiling in terms of Celsius? 100 degrees, right? So minus 100. This part's going to come out negative. That part's going to come out negative right there because it's losing energy to the temperature going down. And this negative out here is going to make it all right. Okay? Equals mass of the cool water, 490. Specific heat of water, C, and it's going to cancel out for me, times delta T. Oh, thank you, 0.49 kilograms. Change in temperature. Final, what I'm looking for, minus initial, 22. Now, those two T finals are the same. Those two T finals are the same. Why? Good. They're together in the same container, right? And they're reaching equilibrium. That means they reach the same final temperature, right? So that's the same, and now it's just out, right? Divide by C, and C's gone. C's canceled. Do I need to do that for you? Yes. Okay. So now, let me try to clarify this. Negative 0.340 times TF minus 100 equals 0.490 times TF minus 22. Yes. So the negative out here, I stuck with 0.34. Let's just say I need to do next algebraic with somebody. Distribute. Good. It's going to work out to where this number is going to be lower than 100, right? And it's going to be higher than 22. We already had that idea in mind. Okay, so let me distribute now. So I got negative 0.340 TF minus, negative plus, what's 0.340 times 100, somebody? So you don't need a calculator. Maybe you do need a calculator.
340.
Very good. 2 zeros mean you're going to jump your decimal place twice, right? Once, twice. It would be 340 if it were 3.4, right? Yeah. Yeah. Okay. Equals 0.490. And maybe you need a calculator for the next one. 0.490 times 42. Oh, I forgot my TI. I'm sorry. 0.78. All right, now I need group-like terms. Okay. So I'm going to bring the 10.78 over to the other side. That will give me 44.78 equals, and I'm going to move this guy to the other one, 490 TF plus 0.340 TF. Line and divide, right? TF equals 53 point what? 95 degrees Celsius. Let's check our sig figs. I got 2, 2, 2. I only get 2. This becomes 54. questions about that before we do a problem. Tricks behind this. The energy lost by one is the energy gained by the other. And the final temperatures will be the same. Those are your two tricks. Okay, I want you to try the next one. I want you to try the next one.